Introduction, right? Like version. Okay. So this is a presentation for our water jet rocket. We are Fernanda, Greta.
Ronaldo?
Okay.
Okay. And basically the objective of this project was for us to see the principles of fluid dynamics applied in a real life scenario and to compare the results, like the theoretical results and the practical results. And because of this, the aim of the experiment was to understand the application of the mechanical fluid principles and also the relationship between the rocket design, the water expulsion, and the thrust generators.
Okay, the materials and equipment used for the launch pad was PVC, PVC elbows, PVC T-connections, PVC plugs, plastic straps, duct tape, cardboard tube, valve for inflating balls, and PVC cement to connect the pipes, and also a 3-liter plastic bottle for the rocket.
Okay, and the procedure that we follow all throughout the project was first we started off with research. We did a theoretical background. We learned a little bit about rocketry and its beginnings, and also about the formulas and all the theory behind the physics that we were gonna see applied. Then we started with the construction, which Ronaldo and Alberto were in charge of. Then we did the testing. We tried with different mass volumes, and we did about 21 launches. Then we analyzed the results in Tracker, and finally we analyzed set results with MATLAB to compare the results that we got with the physics that we learned in class. And from that we could come up with some suggestions that we were gonna delve more into later on, but basically they're all related to aerodynamics.
Okay, so the results that we got were between the Tracker online, because here we chose about one launch of the projectile in this case, but we analyzed all the projectile launches on Tracker online. But here I put the one that got us the more maximum range on this projectile. So here in the Tracker says on the final on the velocity of expulsion of the water was 14.76 meters per second, and here are more in depth. Here is the graph of the motion of the position on X of the trajectory. Here is between 27 and 26 yards. Here 30, 24 meters. Here on the seconds, and the moment when the projectile falls is 2.4 seconds. And here we see that the maximum range in the height of the projectile was 6.159 meters. And here are the results with all the water radium of the projectiles. And we selected the one that was with 800 milliliters, because here we can see that that on the range was 24 meters of the range.
Here we have the analysis for that launch. That first we got the velocity of the water extraction. That was got solving for the velocity in the Bernoulli's equation that got us something similar to Torricelli's formula using pressure of 30 psi and the atmospheric pressure and a difference of height of 15 centimeters. Then in the next slide we use the Tsiolkovsky equation to get the final velocity of the for rocket. We use some data like the water extraction velocity, the mass, the initial mass and the final mass. That the initial was the sum of the water and the bottle, and the final was only the bottle that was 21 grams, and the water was 8,000 grams. That is 0.8 kilograms, and then we got we were supposed to get a final velocity of 53.52 meters per second, but as you can see in the graph, we got something like 12.8 due to some problems such as aerodynamics or the drag force that we will talk about later. Then we made some analysis about the kinetic energy and the potential energy. That was done with MATLAB. That got us, the red line is the kinetic energy, that as you can see is similar as the one that Tracker gives us. That is like a curve, a parabola, and as you can see it is really realistic because in the initial the launch in the initial time we have the higher kinetic energy due to the low position, and in the final is also a high kinetic energy due to the position.
Okay, so in our conclusions were that we saw a significant discrepancy between the practical results and the theoretical results expected because of external factors that we hadn't considered when building the rocket. Some of these are the imbalance of the weight. Once the rocket ran out of water, then it was very light, so the air pulled it down, and so it couldn't complete its expected trajectory. So if we had put a little bit more of weight at the point or at some point, then it would have achieved something closer to it. And that's why also the velocity decreased also because of some factors such as like the drag force that Ronnie mentioned and the friction once it falls to the ground. And that's why our more efficient results were attained with a 50% water ratio. So it was the most balance we could achieve, and that's why our results were better. And some factors like not only the drag force but also the direction of the air, which was literally opposite to the direction of our launch, so that also pulled it backwards. And we saw that this way we can take this into consideration for future projects and to improve the aerodynamics that will help us to obtain more accurate results.
Okay, so on summary, the errors and limitation that we got. First off, on the errors, we have a deficiency of aerodynamics that we talk about. Because of the drag force, we haven't an aerodynamic design. So the leak of the wind is going to be pushing out the object because we have a flat surface. And here on the unintentional leakage, because of the PVC and the water wasn't an enclosed system, while being put pressure, it got leaks of air and pressure. So the launch is going to it isn't going to be as realistic as possible. And then here on the materials that the more materials than we expected. Because of the cost, we expected that there were a little materials, but during the experiment and during the launches, we started to get more materials and other projectiles because we have an initial projectile that was taking into account these aerodynamics, but because we cut off a part of the rocket, it was leaking also water and pressure, so it wasn't going to be accurate. So we purchased another liter of water or plastic, and that's why we have more materials and tape and other stuff. And here also the rocket was too light without water. So in this case, with the drag force and the center of mass wasn't enough to not being pushed to the wind and the force of the wind. So it's going to be backwards and also rotating the object because they didn't have a center of mass. So it's going to be rotating and changing their directions. And here the limitation that we got was of wind conditions because we didn't know where the direction was going to alter this analysis, and also the force. And because of materials, because we have a limited budget as a team, so it's kind of limiting. And also the time for testing, because it was only 1 day to be all the 21 launches. So at the final, we didn't change the design of the projectile as we wanted to be with this aerodynamics taken into account.
And now about these questions, the experiment allows us to compare theoretical and the real life findings. And thanks to this, we realize the importance, we understand the importance of taking into account more factors than the theory let us know, tell us about, especially when it comes to developing a new product or just upgrading a prototype.
Well, there's no difference. Thank you very much.
So can you just tell me how you did that Simpsons calculations using the Simpson?
Yes, okay, so the Simpson calculation we did with MATLAB. This is not the code for the Simpson calculation, but we first started choosing our n, and the teacher told us that it has to be even number, so we chose 10 because we wanted to improve the accuracy. And we basically used an if and some vectors in MATLAB so that it could keep the values stored and then plot them in a graph. But basically what we did was to multiply our our delimited like step times the function of the movement like evaluated in the initial point, and then we did that with all of the points, but we alternated the constants. It was like 1 and then 2 and then 4 and then 2 and then 4 eventually until we got to the last result, which was multiplied by 1, and then we plotted in MATLAB, and that's how we got like our estimate.
So what is the difference between Simpson and trapezoidal?
It's mostly about its accuracy.
Yeah. Since Simpsons has more like steps, it makes it more accuracy because trapezoidal is only like height plus height in the function multiplied by the difference in step that gives us like less accuracy instead of Simpson that is like it takes two points that will be like multiplied like 4 times and 2 times that give us like more accuracy because it takes more like an average.
Yes, also what happens with the trapezoidal method is that, for instance, in the rectangle, we can either know if it's an underestimate or an overestimate based on whether you choose like the left, right, or the right side. And with the trapezoidal, sometimes the value that you get is like below the actual value, and sometimes it is above the actual value. So it is really hard to tell whether you're getting like closer to the value, but you're over it or under it.
And also because the Simpson is taking into account the quadratic like states of these slopes between the variables, so it's going to be more exactly like the rectangle only use like a part of it, so the Simpson is going to be like calculating all the form of these changes.
Yeah, it's trying to make a parabola between 2 points that give us like more accuracy because takes like these 2 points and make like a parabola between them, and then takes these 2 points and make another parabola, and like that in all the function.
Yeah, like really what the Simpson method is tries to do is like to fit the best possible with using only parabolas, so that's the way. And the trapezoidal, as she explained already, like they are all straight lines, so it doesn't fit in a lot of data.
Consider the intervalues.
Yeah, like values, they just create a cup of trapezoid, and this is this method doesn't. It creates parabolas, so it can fit better in each like part of the data.
Very good. Okay, so now you can upload that's it. And now you can upload the evidence as like the video that you recorded and presentation in Evernote.
Okay,
Okay,
thank you.
thank you.
Thank you,
All the
teacher.
best.
Thank you.